Okay, so welcome to the second lecture. We're going to go through some basic results in topology, and the proof will be skipped, and we'll just listing out the theorems and results. Okay, basically a lecture of reviewing. Okay, so metric spaces. A metric space is a set with a metric function such that it satisfies these four properties. Okay, and we define an open ball and a closed ball, right? And a metric space, a set is open if for each set there is a ball contained in the set G. And we have that the empty set entire space is open, finite intersection open sets is open, and arbitrary union of open sets is also open. Similarly, we have the definition of closed sets is defined as the openness of complement. And by De Morgan's law, we have the following results. And we can also define the interior of a set, which is the union of all open sets that is contained in A. And the closure of A is the intersection of the closed set that contains A. And the boundary of A is defined as the closure of A intersect with the closure of A complement. So A bar is closed and interior A is open, right? This is arbitrary union open sets, and this is like an arbitrary intersection of closed sets, right? And this is also the largest open set contained in A, and this is the smallest, the closure of A is the smallest closed set that contains A, right? And we have a list of propositions, right? Let me just read through them. Like, if it's open, if it is equal to its interior, set is closed, if it's equal to its closure. And we have these following formulas that I'll leave you to verify them, okay, if you want to. And the union of closure is the closure. The closure of union is the union of the closures. And the set is in the interior of A if and only if, right? This is definitely, like, you can check this immediately, right? And it says the closure if and only if for any neighborhood it intersects A, right? Okay. This is very important, right? I would say this is like one of the key characterization of closure, right? To prove this, right? You say if x naught is not an A bar, right? Then we have this is contained entirely in x this, right? Something like this, right? And you can move on to that. But anyways, a subset is dense if the closure is equal to the entire space. So what we have here is that for any x, right? For any x and for any ball set in x, there exists A that is an A and it's also in the ball, right? This is like the key characterization, the density, right? And the connectedness, a metric space is connected if the only subsets that are open and closed at the same time are the empty set in the entire space. And we say a subset is a connected subset if the metric space is connected, right? So here we have the relative topology or the subspace topology. And the equivalent formulation is that if they're disjoint percents A, B, such that they're non-empty and they constitute a separation of X, right? And we have that a set in the real is connected if only if it is an interval. So we're gonna prove, okay, we know, we skip the proof of AB is connected. We skip this. I won't, but here's the proof of the connectedness of an interval. And for the converse, if it's connected, we prove that okay, we want to show that connected implies is an interval. Okay, so we prove by contrapositive. Suppose it's not an interval, then we show that is disconnected. Okay, so suppose x is not an interval, then what we mean is that we can find x and y and also z that is not an x such that it lies between them, right? Because you are not an interval, right? So you can find 2 points. Like an interval, it looks like this, right? Because if you're not an interval, right, then definitely you can find x and y such and a z that is lies between them, that does not belong to x. So then we can just, for the z, we consider these 2 sets. They're open in x, right? They are open in x within the substrate topology, and they are non-empty because x isn't this, y isn't this, right? Right? They're obviously disjoint, and their union is obviously x, right? Therefore, we have a separation of x, which means that x is not connected, it's disconnected, right? And we say a subset of a metric space is a connected component if it's a maximal connected subset of x. So the maximal element in a partial order set, right? That is these connected and no connected subset of x that properly contains D. This is basically the definition. This is basically the definition of maximal element. And here's an example of components and whatever, right? And we have a lemma is that for a collection of connected subset that shares a common point, then their union is also connected. And here's the proof. Also, a metric space, then every point is contained in a connected component, and different components are disjoint. And we also have any set, if A is connected, for any set B that's between A and A bar is also connected. This gives this result. If C is a component, then it's closed, right? Because first of all, C is connected, then C bar is also connected. Because if C for any B, for any C bar, B connected, right? B will be connected. But what if we just let B equals to C bar, right? So C bar will be connected. But C is a component, right? C is a component. So C bar cannot properly contain C, right? So we have C bar and C are equal. And here's an interesting theorem. For any open set, the components are open. For open sets in C, the components are open and there are only countable number of them. So this results for any component of G and let X not be in C. Since G is open, right, so we can find a ball contains in G. But notice that this is a connected set, right? And C is also connected, and X naught is the common point in them, right? So it must be C, which means that this must contain in C. Okay? So C is open. And yes, so if you're not following, I could explain in more detail. For C as a component, right? Component of G, and pick a point X naught in C. We wish to find this thing so we can prove that C is open, right? So X naught in C. But first of all, it's a component of G, so C is a subset of G. So X naught is in G, right? G is open, so we can do this. Now, because this is connected, right? And also C is connected, right? So X naught as the common point, it is connected. So this set is connected, but it must be C because C is a component of G, right? So we must have this is true, which shows that C is open. And there's only components, the number of components is countable because if we just consider all the rational points on the complex plane, right, intersect with G, right? So this is a set of all complex numbers such that A and B are rationals and they lies in G. Well, S is countable, right? So each component of G also contains a point of S, right? So the number component is countable. Sequences and completeness, and metric space, right? We talk about sequences and metric space. Maybe pause and take a look at it. And we have that a set is closed if only if for each sequence in F that converges, then it contains the limit. Right? This is another characterization of closed sets. And we say a point is a limit point if there's a sequence of distinct points such that it converges to X. And here is the reason why we say it must be distinct. Okay. And if we have a proposition that the closure, okay, A closure is actually equal to A union with the set of limit points, right? This is another standard result, and some texts even define the closure as this set, right? And we all know what is a Cauchy sequence, right? And we also know what does it mean by a complete metric space. We have some property about the diameter of a set. So diameter is the supremum of all distance of x, y, and a. So this could be positive. Could be positive infinity. Right? We don't know, but we have that if the diameter of a is less than equal to delta, the diameter of a bar is also less than equal to delta. So here's the proof. It's really not that hard. And we're going to use this lemma to prove the Cantor's theorem. Cantor's theorem is like a big theorem. It is a characterization of complete metric space. So a metric space is complete if only if for any sequence of non-empty closed sets of decreasing closed sets and the diameter of those closed sets converges to 0, then this consists of a single point. So this is a singleton, right? This is a singleton. So this is the equivalent condition of a metric space being complete. And we use, so for this direction, maybe you pause and take a look. But for the converse, we want to show that if we have those blah 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 condition, then we show the metric space is complete. Right? So first we just pick any Cauchy sequence and we let Fn be the closure of Fn be the closure after Xn. Right? So we obviously have this, and they're all closed, right? And because it is Cauchy, right? Because it's Cauchy, Xn is Cauchy, so we can do this less than epsilon for all n greater than n, which means that the diameter of this set is less than equal to epsilon for all n greater than equal to n, right? And because by lemma, this is less than equal to epsilon, implies the diameter of Fn, which is the closure of them, is also less than equal to epsilon. This is precisely by the lemma we just proved, right? If diameter of this, then diameter of closure, right? So this is where we use the lemma. Yes, and the rest just follows, okay? And we have another proposition that for any complete metric space and for any subspace, the subspace is a complete if only if it is closed, because it contains a limit. Okay. Compactness. So the definition of compact space, if only for any collection of open sets, for any open cover of K, there's a finite collection that still covers K. So we can change the problem of infinity to the problem of finite. So this is a very important property, important definition in mathematics, compactness. Okay, and some characterization of compactness, right? A compact set of X is a metric space. Okay, metric space. Compact set of metric space is closed, right? So if you know general topology, compact subset of a Hausdorff space is closed, right? It's closed. And also we have closed subset of a compact set is compact, okay? And we also have the finite intersection property. So we have the finite intersection property, then we can use the Morgan's law or contrapositive to prove that a set is compact if and only if for any collection of closed subset with finite intersection property, the intersection is not empty. Okay? So yeah, and we keep on going. Compact metric space is complete. Right? Compact metric space is complete. Why? Because first we can apply the FIP characterization. We can apply this characterization, and then we apply the second half part proof of the Cantor's theorem. Okay. Okay, so if X is compact and every infinite set has an limit point, so this is like we have a key theorem about compact sets, which is this one. Okay. So I'll just assume that you guys already know. Space is compact if it's limit point compact and it's also sequentially compact, and we also have it is complete and totally bounded. Okay. So this is some knowledge that you should know. You can all find the proof of it in my general topology series. Right? Heine-Borel, very famous. Right? A subset of Rn is compact if only if it's closed and bounded. We talked about continuity on metric spaces. I'm sure that we are familiar with this already. And yeah, some characterization of continuous functions. Maybe just take a look at this. And yeah, this is interesting. For any continuous function and the linear combination of, or the product of continuous functions continuous, and even the quotient. The proof is just by sequential characterization of limits. Right? Composition of continuous functions continuous, and uniformly continuous, we all know that. Lipschitz function, right? Lipschitz function is basically here, right? It's here. So Lipschitz function is automatically uniformly continuous, and if it's continuous on a compact set, then it's definitely uniformly continuous. And we also have the definition of a distance from a point to a set, right? Which is the shortest distance of all dxa, where a is an a. So we take it as an infimum. We can take this because we're working with real numbers, right? And yeah, some proposition of the distance between two sets, and the proofs are, so this is the proof of part A, this is the proof of part A, right? And this is the proof of part B and part C. Part B and part C. Okay. And yeah, the continuous function preserves compactness and connectedness. Yes. And we have a corollary, right? Intermediate value theorem. We all know this. And the connected set, right? And yeah, and the extreme value theorem, right? And yeah, this is again an extreme value theorem, right? And yeah, this is another corollary. The corollary of the extreme value theorem. And this is again an application of extreme value theorem. And again, we define the distance between two sets, which is again the infimum of distance between A and A, B and B for all A, B. We take the infimum. Right, this distance between two sets. And yeah, there's another key theorem. For any non-empty disjoint set with B is closed and A is compact, then their distance will be positive. So the distance between closed sets and a compact set will be always positive. Right, and the proof, basically, we define the function as this, right? As this is a continuous function, right? A and B are disjoint. So B is also closed, right? Which means that f of A will be positive for each A and A, right? Because B is closed, right? B is closed, and you pick a point here, you can find a ball in that, right? So the distance will be positive. Positive distance will be positive. And we apply the EVT because run through all the compact sets and so on. Uniform convergence, right, is another type of convergence, right? Study this in topology or even analysis. And we have the Weierstrass M-test from calculus, right? The proof of Weierstrass M-test is again not hard, right? So one thing that is worth noting is that one thing, if we just read through this proof. So the M-test, so let f and x to be the partial sum, right? Then we show that fn and fm are Cauchy, right? This sequence is Cauchy and C. Thus it converges, right? Because C is complete. So we induce another function, right? This gives a function from x to C. Now fx minus fn x, which is equal to this from n plus 1 to infinity. This is the remark that I wanted to give, right? And this inequality still requires some explanation, okay? Because first we have each mn is positive, right? So what we have is that P of unx, we have this will be less than equal to mk, right? Mk. And this will be less than equal to what? The limit, right? This converges, right? So, which means that this whole thing is a monotone but bounded sequence, right? So this converges, right? So we have the limit exists, which means that we have this converges, and the limit is still, the limit is still less than or equal to this, right? So even this still boils down to the first year stuff, right? If we have if an converge, right? And converge, say if an converges to A, Bn converges to B. No, an converges to A, and An less than or equal to B for all n, then A is less than or equal to B. Okay, so this is the thing that you might learn in first year, right? So try to prove this if you forgot, right? So this explain this, like the limit is all the terms here is bounded by this. So the limit is still bounded by this. So this explains this inequality, right? And and what we did here and also here, we see that, oh, this is convergent, which we can make this arbitrarily small for all n greater than n, right? And yada yada yada. And so this gives a remark that if AK, the series converges to S, then if we start from n plus 1, this is another series, right? And this series converges to S minus a finite sum. Right? Do you see what is the claim behind this? Right? If the original series converges to S, then this series, starting from n plus 1, this is another series, it converges to S minus a finite sum. To verify this is just by definitions, right? Because this thing is equal to this by the definition of a series. And this thing is from 1 to m minus from 1 to n, right? Because we're from n plus 1 to m, right? So this is the limit of this thing. And we know that this converges, this is a finite sum, so we can split the limit. And this goes to s minus this remains the same, right? So this is why we have this is true. And yeah, this is everything that I would like to review for so far. And the next time we're going to start talking about complex differentiation. Now I'll see you guys next time.